Frequency division multiplexing. If ordinary FDM is used on the frequency band owned by an operator, the carriers must be separated by a guard band to avoid interference. This guard band is wasted frequency bandwidth. But by using OFDM, orthogonal frequency division multiplexing, the subcarriers are orthogonal, meaning that they do not interfere with each other, and can therefore be put very tightly together. To be able to reach orthogonality, a Fourier transform is used. In principle, the frequency of each subcarrier must be a multiple of the delta frequency between neighboring subcarriers. All subcarriers covering the frequency band form one OFDM symbol, with the length and time given by 1 over delta frequency. Let's continue with the defined frequency bands for LTE. The minimum band is 1.4 MHz. The defined value for the delta frequency in LTE is 15 kHz. Hence, for the 1.4 MHz band, the OFDM symbol consists of 72 orthogonal subcarriers. There are 5 more spans of bandwidth up to 20 MHz. In the last case, there are 1,320 subcarriers making up the OFDM symbol. In LTE, it has been decided that subcarriers should be arranged in groups of 12. Each group forms a physical resource block. Each PRB is then 180 kHz, since 12 times 15 is 180. As we can see in the table and the picture, the 1.4 band consists of 6 physical resource blocks. Filling in the rest of the table, we see that the largest band holds 110 physical resource blocks. The access method used in LTE is built on sharing, not only done in frequency domain, but also in time. Hence, next a look at frequency and time. The subcarriers are lined up along the frequency axis, and the OFDM symbols come after each other on the time axis. Where the time for one OFDM symbol is given by 1 over delta frequency, a requirement to enable orthogonality. Going back to the physical resource block, it is not only defined in frequency, but also in time. The definition of one physical resource block is half a millisecond in time, and as we saw earlier, 180 kHz in frequency. The steps of half milliseconds are also referred to as slots, and 2 slots form a subframe. In the normal solution, there will be 7 OFDM symbols transmitted within 1 slot. This picture shows the time frequency matrix, with the smallest bandwidth 1.4 MHz with 6 physical resource blocks. This is one physical resource block built up by resource elements. The procedure used to decide how the radio resource shall be used is called scheduling, and it's the eNode B that is in charge of that. Scheduling is based on a time step of 1 millisecond, the time of one subframe, or a pair of physical resource blocks. In this cell, there are 2 UEs, the blue and the red one. During the first millisecond, the eNode B decides that the whole bandwidth is allocated to the blue UE. The information to be sent to one UE in one subframe is packed into one transport block. During the next millisecond, the eNode B decides that 1/3 of the radio spectrum is allocated to the blue UE, and the rest, 2/3, to the red UE. The access method in LTE is based on sharing in frequency and time. 2 UEs can receive or transmit during the same time, but then they are separated in frequency, or they can receive or transmit on the same frequency but not during the same time. The smallest allocation unit in LTE is one pair of physical resource blocks. This pair cannot be shared amongst several UEs. So, with a bandwidth of 1.4 MHz, the largest number of UEs during 1 millisecond is 6. When an eNode B allocates radio resource to a UE, it shall take modulation into account. In LTE, there are 3 different modulation schemes defined for the user plane. The modulation scheme used depicts the throughput. Low modulation scheme used leads to low throughput. High modulation scheme, high throughput. But let's start with binary phase shift keying to explain the concept of modulation. When using BPSK, the radio wave can have 0 or 180 degrees phase. These 2 phases can then represent the digits 1 and 0. The modulation symbol, the radio wave, is sent over the air and will be interpreted by the receiver as digit 1 and 0. The lowest modulation scheme used for the LTE user plane is quadrature phase shift keying. In this solution, 4 phases are used: 45, 135, 225, and 315. With 4 phases, each modulation symbol can represent 2 digits, since 2 to the power of 2 is equal to 4. Since each radio wave now can be interpreted as 2 digits, the throughput, when using QPSK compared to BPSK, has doubled. When using 16 quadrature amplitude modulation, both phase and amplitude is used. Both the red and the green dot have 45 degrees, but different amplitude. With this solution, each modulation symbol can represent 4 bits, since 2 to the power of 4 equals 16, and the throughput has doubled again. The last modulation scheme, used in LTE, is 64 QAM, with a throughput 3 times higher than QPSK, since each modulation symbol equals 6 bits. The drawback with a high modulation scheme is that it requires good radio environment. Since it is so complex, it is easily disturbed. With QPSK, the throughput is low, but the signal is robust. This is a network with mobile units, leading to that the modulation scheme has to be changed when the radio environment varies. The UEs will, when a radio connection is established, report to the eNode B which modulation scheme to use. This is called the Channel Quality Indicator. Learn more of CQI in the Spec Tool chapter Physical Layer 36.211. Let's go back to the LTE radio structure. During the second millisecond, the eNode B allocated 1/3 of the bandwidth to the blue UE and 2/3 to the red one. Each resource element carries 1 modulation symbol. Let's assume that the blue UE has quite good radio conditions, and therefore it can utilize 16 QAM, hence 4 bits per resource element. But the red mobile suffer worse radio conditions and utilize QPSK, thus only 2 bits per resource element. The radio resource allocated to the red UE is twice as large as the blue area. But since the throughput for QPSK is half of 16 QAM, the number of bits carried over the air interface is the same. The largest number of bits that can be carried in one transport block is 75,000 bits, presuming the widest frequency band 20 MHz and the highest modulation scheme 64 QAM. Please notice this is valid for uplink transmission. For downlink, it is more complicated.